In this section, I'm going to show how the temporal dimension, or the time part of space-time, emerges by taking the sum of entropy of both the macroscopic physical systems that we can observe in the universe and the particles those systems are made of. Again, we're going to start off with some well-established prerequisites. In this section, that's going to be how entropy establishes zero of time. I'm going to touch on some of the broad strokes of general relativity, how certain particles distort space-time so they move through the three-dimensional space as well as the unidirectional dimension of time, what kinds of particles experience the dimension of time, and what it is about those particles that enables them to experience time. And then we conclude the section by taking what we have covered in the second and third sections together. By thinking of excitations of the quantum fields that are the fundamental particles, by thinking of these particles as oscillating systems and accounting for them when considering the entropy of large systems, I will show that time emerges as a unidirectional dimension that is established by the conservation of entropy. It's generally thought that entropy is the reason that the universe has a one-way arrow of time. The second law of thermodynamics says that entropy will always increase in any closed physical system. This is taken to be an overwhelming probability rather than an unbreakable law. So as a system becomes more disordered, it becomes more unlikely that it will return to a more organized state. As the system evolves, the probability that it will evolve towards the probability is that it will evolve towards a state of equilibrium. And this is because there are many more ways the particles and energy can be distributed evenly throughout the system than not. As the system evolves, there's a higher probability that the next unique configuration of that system is going to be one that is closer to equilibrium. The odds that a system might evolve briefly to a state that is slightly less like equilibrium once or twice, that might be unlikely, but it's fathomable. The odds that this would happen over and over again, so there's an observable shift towards a more organized state, are phenomenally low. What this means is that as the system evolves towards equilibrium, it becomes more unlikely that it will evolve to a state of lower entropy. Particle only experiences time if it has intrinsic mass. In order to experience the dimension of time, a particle must distort space-time so that it kind of gets sort of drawn down into the temporal dimension. That's one way to think of it. Gravity is the force that distorts space-time. It's also the force of attraction between massive bodies. And this is really two ways of saying the same thing. It's because gravity doesn't pull massive bodies together. It warps the geometry of space-time in the presence of massive bodies, which causes them to come together. Think of setting two bowling balls on opposite sides of a trampoline. They're going to roll together in the middle of the trampoline. And this isn't because they pull towards one another. They push down against the fabric of the trampoline, distorting its geometry so that the path of least resistance is not for them to then stay on the opposite sides. The path of least resistance becomes the bowling balls rolling together in the middle of the trampoline. For a particle to have a gravitational effect, it needs to have mass. Therefore, only particles with mass experience time. The kinds of particles that have mass are fermions. Fermions are the fundamental particles that all matter is made out of. Anything that exists in the universe that is tactile or has any substance to it, fundamentally, that stuff is all made of fermions. Because fermions are the particles that have mass, they are the particles that experience time. And it's worth noting that there are some bosons that have mass and therefore experience time. But they basically pick up their mass through their association with fermions. A detailed explanation of this mechanism isn't really relevant to this presentation, so I'm not going to spend much time talking about it. It doesn't change the idea that this kind of knotted structure of a fermion is where they get their mass from. But it's just worth noting, because I'm sure that there are people that are watching this are aware that there are bosons with mass. And now we are ready to prove the conclusions for this section of the presentation. So given these premises, 1, for any physical system to exist, the fundamental components of that system must also exist. 2, any physical system that can be observed to exist in the universe must include fermions as fundamental components of that system. 3, we've established that as fermions exist over time, they can be viewed as fundamental systems evolving in states of decreasing entropy. And 4, as any macroscopic system evolves to states of higher entropy, obeying the second law of thermodynamics and in accordance with the arrow of time, the fundamental components of that system are evolving to states of lower entropy. We are led to the conclusion that the arrow of time is established by the exchange of entropy from the particles that a system is made of to the system that is made of those particles. Rather than holding the view that entropy increases in any closed system, we can adopt the view that as any physical system evolves macroscopically to a state of increased entropy, the fundamental components of the system evolve to states of low entropy. When accounting for the decreased entropy of the fundamental components of any macroscopic physical system that exists in the universe, we should conclude that entropy can rightly be seen as value that is conserved over time. This conservation of entropy is the causal power for the emergence of a unidirectional dimension of time.